Welcome to N34, the next discussion dealing with the properties of solutions, focusing on Raoult's law. This equation and concept is on your equation sheet. So if solutions do show up on the AP exam, which this topic is not guaranteed, Raoult's law is probably going to show up. So what is it? Well, Raoult's law, the presence of a non-volatile solute. So non-volatile is making a notion that it is a solute that is a solid. Non-volatile are solid solutes that lower the vapor pressure of the solvent. We see that through this equation where the observed pressure of the vapor pressure of the solution is equal to the mole fraction of the solvent times the pure vapor pressure of a pure solvent. So again, P solution is observed vapor pressure of the solution, mole fraction of the solvent, and the vapor pressure of the pure solvent. So this equation, again, is on your equation sheet. Any questions regarding it? Alrighty then. So, vapor pressure lowering. What's going on? What is causing the vapor pressure to be lowered or reduced? The vapor pressure of a solvent in a solution is always lower than the vapor pressure of the pure solvent. So anytime you dissolve something and create a solution versus just the pure solvent itself, the vapor pressure will be lowered. The vapor pressure is directly proportional to the amount of solvent in solution. So the more solvent you dissolve, the greater the vapor pressure lowering is going to happen. So the difference between vapor pressure of the pure solvent and the vapor pressure of the solvent in solution, again, is our reference to vapor pressure lowering. So got to figure out what is going on versus, figure out what is going on between solvent by itself versus a solution with solvent and solute. So the change in vapor pressure, again, pure solvent vapor pressure minus the observed solution vapor pressure, which then has to equal Raoult's law. So the equation, just another way of looking at it in order to figure out, what's actually happening. It's a change. So if College Board asks for the change, you can't forget to do that subtraction. It's kind of a key thing students tend to miss is they have the vapor pressure of the pure solvent, they solve for the vapor pressure of the solution, and they just forget to subtract to find that change. Questions? Okay. So some diagrams, lovely diagrams. We love our diagrams. So the vapor pressure of a solvent above the solution is lower than the vapor pressure of the pure solvent. Again, we've said that before. We know an equilibrium exists between the solution or solvent and right above that liquid is your vapor pressure. So some solute particles replace some of the solvent molecules at the surface. Pure solvent establishes this lovely equilibrium. So again, a lot is going on with what's happening at the surface of your solvent or solution. When you go from a pure solvent and then as you start adding solute particles, things start changing. So the addition of a non-volatile solute, again, reminder, non-volatile is a solid solute that is dissolving, reduces the rate of vaporization, decreasing the amount of vapor. So that equilibrium is going to shift due to one of the rates is being reduced. Now, as you can see with the red and the blue atoms, there's some interactions taking place there. There are IMFs that are playing a role. This is where IMFs continue to affect what's going on. So we can look at it from the perspective of the type of IMF, the similarity or dissimilar are the IMFs between solute and solvent that can help explain what is happening with vapor pressure. So as you add a solute and make a solution, eventually equilibrium is going to be reestablished, but a smaller number of vapor molecules, therefore vapor pressure will be lowered. So we've seen, starting with a pure solvent, as we add solute, the equilibrium is adjusted, reducing the rate of vaporization, therefore lower vapor pressure eventually is established once the equilibrium is reestablished as well. So we can kind of explain what's happening and why it's occurring. Questions with vapor pressure of solutions? Okay. All right, moving on to liquid-liquid solutions in which both components are volatile. Again, remember, volatile just tends to mean a lower boiling point. We're looking at it from perspective, this whole idea of non-ideal versus ideal, kind of like the ideal gas law. You know, no gas exactly behaves ideally. No solution, in this sense, will actually behave ideally. So again, it's going to be a non-ideal situation. So because we have liquid-liquid solutions where both liquids individually have their own vapor pressure, we have to modify Raoult's law. Now again, this equation is not on your equation sheet, but because Raoult's law is on your equation sheet, you can then come up with this one on your own. So same things are here as they were with Raoult's law. P naught is vapor pressure of the pure solvent, and then pressure of A, pressure of B are the partial pressures, observed pressures. And as you can see, it's basically just Raoult's law plus Raoult's law on the right-hand side of the equal sign, and then based on your mole fractions of the two different solutions. Questions on this equation? All right. So ideal solutions, which again can't really exist, but liquid-liquid solutions that actually obey Raoult's law tend to be considered ideal solutions. Just like you can get gases under certain conditions that can best mimic ideal conditions, but it's never going to be that way. So no solution is perfectly ideal, though some can get pretty close. Just like gases, under certain conditions, some can get pretty close. Now, when we look at the liquid-liquid solution that is made, we got to look at the IMF. Are the IMFs similar or different? In the sense when they are similar IMFs between solute and solvent, we get a negative deviation from Raoult's law. So ultimately, we're getting lower than predicted vapor pressure for the solution. When we use the modified equation, we'll get a number of what we believe the observed pressure should be. But when we actually test it in the lab, we end up getting a lower than expected, which is again called a negative deviation. Again, that is a vocab word that you're going to have to use. Now, why does a negative deviation come about? We already kind of alluded to it. Solute and solvent are similar in their forces of attraction, in their makeup, similar IMFs. Therefore, they're going to be a stronger type of attraction. From a heat of solution perspective, it's going to be large and negative. Remember, we want negative heat of solution, says the solution should form. And especially if it's large and negative, the magnitude, then the solution really wants to happen because of the similar IMFs. Now, conversely, we're also going to have positive deviations from Raoult's law, where we put our calculations in, we get a number, we conduct the experiment in a lab, and we get a vapor pressure that's actually higher than predicted. Well, because of solute and solvent, they're going to be dissimilar with only weak forces of attraction. Now, when I say dissimilar, I'm not saying oil and water, because in a positive deviation, a solution still forms. It's just a weaker attraction between the IMFs having to do with solute and solvent. Because of this weak attraction, particles tend to easily escape those attractions in solution and enter the vapor phase. So you get, again, more molecules right above the surface, which increases vapor pressure. Questions on this? Alrighty then. So, ideal versus non-ideal. Something we got to consider, because ideal solutions, you obey Raoult's law perfectly, which we know can't really happen, but you can get pretty close. So we know that in ideal solutions, the solute-solvent interactions are equal to the sum of the individual particles, solute and solvent interactions. Again, ideal is when they equal each other. So that's kind of a key point there. To have an ideal solution, the interactions between solute and solvent equal the sum of the interactions between solute by itself and solvent by itself. Ideal solutions follow Raoult's law perfectly. So if I plug it into the equation and then measure it, I'm going to get the exact same number. So effectively, the solute is diluting the solvent. If you think about it, the mole fraction of a pure solvent is 1. As you add solute, the mole fraction of the solution, or looking at the solvent specifically, is going to decrease. Kind of like a dilution decreases the concentration. Similar idea in that sense. If the solute and solvent interactions are stronger or weaker than the individual interactions of solute and solvent, then your solution is non-ideal, which again gives us the positive and negative deviations from Raoult's law. Questions on the difference here between ideal versus non-ideal? Alrighty then. So, vapor pressure of a non-ideal solution. Again, looking at it from the interaction perspective, when the solute-solvent interactions are stronger than the individual interactions of solute and solvent, the vapor pressure will be less than predicted, negative deviation, because the vapor pressures of the solute and solvent are lower than what was expected from an ideal point of view. And then conversely, solute-solvent interactions, when they are weaker than the individual interactions of solute and solvent, vapor pressure tends to be more, or positive deviation, than predicted by Raoult's law. Which brings us to our lovely picture. Love me some pictures. So on the far left is your ideal solution, looking at, or figure A, sorry. Notice these lines are nice and linear and straight. So red and blue, individual components, and the purple represents the ideal vapor pressure when you have a solution based on what's the mole fraction of A, is what they're showing. We go to the middle one, letter B. This is where we have negative deviations. So the dashed lines are identical to the figure A on the left, except notice that our graphs go below the line, representing a negative deviation. Conversely, in letter C, gives us our representation of a positive deviation. The vapor pressure of the solution is above the ideal line compared to A. Now, College Board has had you guys sometimes draw the line. Like, they will give you the dashed line, and then based on your understanding of the solution, then you would either draw in a negative deviation or a positive deviation regarding the purple line that you see. They haven't really asked about individual solutes or solvents of the two solutions independently. It's usually asking about when the solution forms, will it be a positive or negative deviation? So again, they would give you the dashed line, and then you would add in the purple line based on your understanding of the type of solution created. Any questions on deviations from Raoult's law? All right. Thank you very much. We'll see you next time. Bye-bye.